Hello. So today I would like to talk about the step buffer overflow. So the buffer overflow is the situation where we are using some probably low level C function or something to write a string or some other variables into a piece of memory that is only a certain length, but we are trying to write something in that's longer than, and it then override the later memory address, and that can cause all kinds of the problem. So today I would like to show that how the step smashing exploits happens. So first thing I want to do is to creating a hello file in my Linux terminal. Is it echo hello world. That all right. Then I can type ls to chat. Yeah, the file is already created successfully. Now I need to compile the code.c. So I will explain what is the code file later. Now I just compile first. Code.c. Yeah. Then I will run it now. So let's have a look what is this file. Yeah, and we can see there's three function inside. So the refile one, this function take the path to a file as a string and return the contents of the file in a C string. And the second one, the fonts, this is the function that's vulnerable to a buffer overflow. It takes a C function, it takes a C string here and write it into internal buffer that is 80 bits long. If the string pass in it's more than 80 bits long, function will just copy it over. So the final one is the main one. The main will read the file from memory and then pass the contents of the file to func, and then display the contents of the file before existing. So we have two local variable here. We can see in the second function we have two local variable, one called the buffer, the second one called the number. So the buffer should have like 80 character, and the character should be 1 bit long, and each number is 4 bits long. When we call a function from like C perspective, what we are trying to do is we create a bunch of local variable. We do some computation on those variable. When we finish the function, we return and resume execution from the call of the function, and it should be man in this case. It continually running man whether you left off. So internally, something like this happen. In order to store them in the machine, that does using a step. It allocate like 80 bits for the buffer and 4 bits for the number and 8 bits for the return address. This whole kind of things used for particular function called the step friend, and in this case is for function. But there's a problem with this code is written. The problem is we use the string copy function, but it doesn't do the bond checkings on arrays or strings. So if we try to store something in buffer that is longer than 18 bits, it also mostly will work. If we make it long enough, we could override the other variable and even the return address here. So it will be terrible. But fortunately, like Linux have free way to to protect the situation happen. So now I will try to enable those 3 features to pretend the situation happen. So the first one is the step protector. The step protector will put between the variable and the return address here. So if you try to override something, the program will check whether it runs, and if it check like it be attacked, then it will throw exception. So now I need to disable it first. So it's GCC doxy follow steps protector. Yeah, it works. And the second one is non-executable steps. By default, Linux not allowed code to be run in the step, so we need to disable that. So it's just add this here. So it's an ES EC step. Yeah, it works as well. So the final one is the JAP space layout randomization. The step puts randomly every time when you run the code, so you can't just hardcode just here. So we can run the program without ASL, without with the comments I set here, so we can get rid of it. Set arch R. One second. Let me chat first. Oh, yeah. One more space here, I think. Yeah. Should be work now. Yeah. So we successfully like turn off all the protections from Linux. So after that, the second thing we need to know is the buffer address and the address of the return address we store at. So we need to know the address here, the buffer address, and the address of the return address in the stop memory. So once we got them, we can calculate the distance between them. And in roughly will be like 84. Then I will have a shellcode here, and between the shellcode and the address of the shellcode we have the padding. Then I will have a shellcode with 48 bits. Then I will using the length between the buffer and the return address. Suppose it's like 100. So if it's 100 and here is like 48, so there are 52 at the padding. So I will calculate things like that and use the shellcode and padding inside it. So the second thing I would like to figure out is the two address we discussed above. So now let's get to find it in the Linux system as well. So now I open the second terminal, and I would like to know what program I'm running in system. Oh, that's too much. Maybe I need to grab the one I'm looking for, is the code, because I would like to know some information for this. All right, so it's grab code. Yeah, and we can see the first one is the program itself, and the second one is the program that I'm running now. And the things we need to pay attention is the second column, which is the process ID, and it's the unit ID of the program. And I will use this one to attach in the use the GDB. So like 3219 is the thing I need to pay attention, because it's the identity of the program. So let's run GDB now. GDB sudo GDB attsh is 3219. Yeah. So now I am successfully to attach, and also I need to set up a breakpoint. Here is then I tell the GDP to continue running the program with the continued command. Yeah, it's continue now. So the GDP will hang out until we go back to the running program and press the enter key to allow it to continue. To do this, I need to go back to the first terminal and press the enter key and go back to the second terminal. Then you will see the breakpoint happens. So there are two commands we need to run in GDP to get the address that the return address is stored at, and the address the buffer is stored as well. So now I need to type info framed, as I guess you know what meaning is. It's to know the staff framed information. So the last line we see here, the rip at blah blah blah, which is the address of the return address. Then the next step we need to do is to know the buffer address as well. So the buffer address just we can get with print buffer address. So yeah, so that means print the buffer address in C language. Then we'll get the buffer address as well here. Then we need to remember the both one. This is buffer address, and this is sorry. And upper one is the rib one is, yeah, it's the return address. All right, let's go ahead. No worry. We type continue. So we go to Alt 1 and say, yeah, all good. Then we go back and we quit this one because we already got our address. Now, the next I want to create an exploit string to put it into the hello file and get the program to read this. The exploit string should consist of the following: the shellcode, which should be at the start of the string, the address of buffer, which should be at the end of the string, so that it overrides the return address, and the computer will start running the shellcode after returning from the function. Some padding between the shellcode and return address, so that the return address ends up in the right place. So like I need to open a third terminal. The first thing I would like to do is to give the permissions to run the script at Linux, because by default it cannot be run. Okay, then I will start to run the script now. So now I put my return address. Let's go back to find my return address. Yeah, it's here. Let's copy it first. And get my buffer address here. Then copy it. Yeah. The final is I add the file names hello here. Then it works. So the next thing is I would like to get the contents of the file. I would like to know what's inside. Yeah, we can see here at the beginning part is the shellcode, and the middle part is the padding, and the final diamond is the return address here. So final, we need to run the program again. Yeah, so that means the exploit runs on my machine. So that's all my presentation. Thank you.